Now that you have seen the new lineup of 1997 cars, let's take a closer look at some of the new technology on these cars. For the 1997 model year, there are some changes in OBD2 information available on the scan tool and the OBD2 drive cycles used to verify a repair. What do you say we look at what these OBD2 changes mean to you in the service bay? Click on that OBD2 button for an overview. OBD2 diagnostic information is displayed on the scan tool in either the General Scan Tool mode or the Mitsubishi Scan Tool mode when using the Multi-Use Tester 2. The General Scan Tool, or GST mode, only displays emissions and powertrain-related information required by the federal government. For all 1997 models, OBD2 P-Series diagnostic trouble codes are displayed in both the GST and Scan Tool modes. These P codes replace the Mitsubishi diagnostic trouble codes that are displayed on earlier Mitsubishi models. And on the new Mirage, several new P codes have been added for engine and transaxle diagnosis. The number and types of codes vary depending on engine and transaxle combination. For example, a Mirage with a 1.5-liter engine and automatic transaxle has 45 P codes available. With the 1.8-liter engine and automatic transaxle, 47 codes are available. If a code is not available in Mitsubishi Scan Tool mode, the Scan Tool will display the code from the GST mode. Along with new codes, additional engine and transaxle service data and actuator tests have been added for the new Mirage, such as a base ignition timing mode, which allows checking and adjustment of the base ignition timing, an idle air control fixed position mode for checking and adjustment of the basic idle speed. On the scan tool, it's shown as SAS mode for speed adjusting screw mode. The engine must be fully warmed up. The scan tool will hold this mode for 27 minutes unless the clear button is pushed. In addition, all 5 automatic transaxle solenoids can be duty cycled to monitor their operation. We'll see more about the transaxles later. In previous programs, we've covered the use of the readiness tests and the OBD2 drive cycles to assist you in verifying that repairs have been successfully completed. A readiness test is completed when the ECM forces a test of an OBD2 monitored system. Access the readiness test mode using the Scan Tool readiness test screen. This screen describes which specific readiness test monitors are available on a particular vehicle. It will indicate whether or not a readiness test has been completed and lists any items that are incomplete. The readiness test screen will change to complete as soon as the test is performed. Often, this will occur before completion of the drive cycle. A readiness test is helpful in verifying that a repair has been successfully completed. The increased sensitivity mode allows the ECM to set a diagnostic trouble code the first time a system or component fails a test. This helps to locate intermittent problems quickly. With increased sensitivity, a brief momentary component failure is easier to detect, and problems that would require multiple drive cycles set a diagnostic trouble code the first time they are detected. If you don't use increased sensitivity mode, you will have to run at least 2 drive cycles to ensure a problem has been corrected. Verifying a repair with the 1997 new models will be faster because the OBD2 drive cycles have been broken into 5 different drive cycle patterns, depending on which systems are to be tested. The drive cycle patterns were designed so that the engine operates under the best conditions to monitor the performance of the particular system you need to test. This is going to make your life easier, so let's step through each of these tests. The drive cycle for the catalytic converter monitor can be completed in 20 minutes or less. You'll run this test if the ECM has set DTCs P420 and P421. With an outside temperature of 14 degrees Fahrenheit or higher and the air conditioning off, perform the test as follows. Accelerate gradually to 45 miles per hour or more. Use D range for cars equipped with an automatic transaxle or shift through to 4th gear with a manual transaxle. Continue driving between 45 and 60 miles per hour for 5 minutes. This allows the ECM to operate in closed loop for maximum catalytic converter efficiency. The brake may be applied if necessary during this period, but only for a few seconds. Decelerate to 35 to 40 miles per hour and then keep the throttle constant by not moving the accelerator pedal as much as possible for 90 seconds or more during monitoring. Next, decelerate for 10 seconds, applying the brake as necessary. Then accelerate gradually to 35 to 40 miles per hour. Repeat 5 times or until the readiness test has been completed. Finish the test by coming to a stop, verifying a completed readiness test, and turning off the ignition switch. The heated oxygen sensor monitor sets codes P130 or P136 if there is a problem. After correcting the problem, verify the repair with this drive cycle. It can be completed in approximately 5 minutes or less. With the engine running and fully warmed up, coolant temperature 176 degrees Fahrenheit or more, and an outside temperature of 14 degrees Fahrenheit or more, turn off the ignition switch to reset the drive cycle. Then restart the engine and accelerate to 35 to 40 miles per hour. Use D range for cars equipped with an automatic transaxle or shift through to 4th gear with a manual transaxle. Drive between 35 and 40 miles per hour at a constant speed by not moving the accelerator pedal as much as possible for 2 minutes or more. This allows the ECM to operate in closed loop, where oxygen sensor output is predictable. Try not to turn the steering wheel suddenly. After 2 minutes, come to a stop, check for a completed readiness test, then turn off the ignition switch. If there is any problem that would prevent closed-loop fuel control, this readiness test cannot be completed. If you are correcting a P140 DTC, the exhaust gas recirculation or EGR system, the test should take about 10 minutes or less. Turn off the ignition switch after you've fully warmed up the engine. The coolant temperature should be 176 degrees Fahrenheit or more, with an outside temperature of 41 degrees Fahrenheit or more, and the air conditioning should be off. Restart the engine and accelerate to 35 to 40 miles per hour. Use D range for cars equipped with an automatic transaxle, or shift through to 5th gear with a manual transaxle. With the engine running between 2,000 and 3,000 RPM, drive for 20 seconds, then decelerate until the engine is running at 900 RPM. The EGR monitor operates during deceleration, when intake manifold vacuum is steady and predictable. Do not apply the brake and do not disengage the clutch on manual transaxle models. During this portion of the test, try not to turn the steering wheel suddenly or turn on the headlamps. Repeat the acceleration and deceleration procedure 8 times or until the readiness test has been completed. Fuel trim monitor drive cycle test takes 35 minutes. During this test, the ECM will check for problems that set DTC P170. With the engine running and fully warmed up, coolant temperature 176 to 207 degrees Fahrenheit, and an outside temperature of 14 to 140 degrees Fahrenheit, turn off the ignition switch. Restart the engine and accelerate to 55 to 60 miles per hour. Use D range for cars equipped with an automatic transaxle, or shift through to 5th gear with a manual transaxle. Drive between 55 and 60 miles per hour for 30 minutes or more and vary the throttle angle by moving the accelerator pedal every 2 minutes during monitoring. During the test, you may apply the brakes, but avoid rapid accelerations or decelerations. When you are finished, verify a completed readiness test. This test allows the ECM adaptive memory to adjust to a steady and predictable set of driving conditions. A final drive cycle is 10 minutes or less, and it monitors all other emissions-related components on the vehicle. As with the other test, the engine should be fully warmed up, coolant temperature at 176 degrees Fahrenheit or more, and an outside temperature of 41 degrees Fahrenheit or more. Cycle the ignition switch and restart the engine and accelerate to 35 to 40 miles per hour. Drive for 5 minutes at this speed using D range for cars equipped with an automatic transaxle or 5th gear with a manual transaxle. Minor acceleration or deceleration is not a factor during this test, and slight braking is okay. Come to a complete stop and shift to park with an automatic transaxle or neutral with a manual transaxle. Allow the engine to idle for 5 minutes or more with the lights, coolant fan, and all accessories, including the air conditioning, off. Verify the completion of the readiness tests. In general, if a readiness test is completed and no DTCs are present, and the malfunction indicator lamp does not light, the repair has been successfully completed. If any DTCs are still present, follow the diagnosis and repair procedures in the service manual. Now let's look at the technical changes for the new 1997 Mirage. Fortunately for us, those changes are just a click away. Technology sure is wonderful when it works, and the Mirage is an example of finely tuned technology that works. In fact, the most significant technical changes to the 1997 model lineup are on the Mirage. Under the hood, you'll find that the mounting direction on both the 1.5-liter and 1.8-liter engines has been changed 180 degrees, from west-east to east-west. This allows for smoother operation by reducing acceleration and deceleration shock. Mounting the engine from east to west also allows for a reduction in moving parts within the transaxle, resulting in quieter operation and less weight. Technical advances on the 1.5-liter engine include a redesigned cylinder block. The new block has been reinforced in several areas to increase rigidity and reduce engine noise. To allow for a more stable engine warm-up and cleaner emissions, the thermostat has been moved from the outlet side of the cooling system to the inlet side. The cylinder head bolts have been redesigned to maintain uniform tension after installation using a plastic angle tightening procedure similar to what you've seen on other Mitsubishi models. Technical improvements on the 1.8-liter engine include an aluminum brace to increase the rigidity between the engine and the transaxle. This brace helps to reduce powertrain noise. The oil pan is now made of low-noise steel plate for a quieter engine, and the engine oil filter has been relocated from under the exhaust manifold to the front of the engine for easy access. Remember, do not install an automatic transaxle filter here by mistake. The exhaust manifold material has been changed from cast iron to stainless steel to reduce weight and to lower engine emissions by providing faster activation of the catalytic converter when it is in a cold state. The ignition system on the 1.8-liter engine has been upgraded. The ignition coils mount directly on the number 1 and number 3 spark plugs, and spark plug cables connect the number 2 and number 4 spark plugs to the secondary terminals of the ignition coils. This system simplifies the secondary wiring and makes it more reliable. The ignition power transistors are now built into the ignition coils. The 1.8-liter engine now has a distributorless ignition system and a new style camshaft position sensor with the same design as the new camshaft position sensor used on the 2-liter Eclipse turbocharged engine. An ignition failure sensor has been added to monitor primary ignition system operation. As ECM control signals turn the power transistors on and off, the failure sensor monitors the ignition coil primary circuit operation. Output from the failure sensor is sent to the ECM and the tachometer. You'll also find that the connector for base ignition timing inspection has been eliminated, and a base ignition timing mode and idle air fixed position mode, called SAS mode, has been added to the scan tool actuator test functions for the Mirage. These are used in place of the ignition terminal when performing basic adjustments. Both of these operate for 27 minutes or until the clear key on the scan tool is pressed. The ignition system crank position sensor is basically the same as the 2.0-liter turbocharged engine used on the Eclipse. The camshaft position sensor is located at the rear end of the cylinder head. It's mounted on and rotates with the camshaft. While this Hall effect type sensor produces a square wave signal similar in design to other Mitsubishi camshaft position sensors, the signals are generated differently. On previous designs, the Hall element and a magnet were mounted on either side of a magnetic shield plate containing cutouts. With the new design, the Hall element and the magnet are mounted on the same side of a sensing vane. As the vane passes across the front side of the Hall element, the flux from the magnet passes through the Hall element, causing it to generate a voltage. When the vane is not passing across the front of the Hall element, the flux does not pass through the Hall element and no voltage is produced. The result is a 5-volt square wave with a reference pulse. Speaking of Hall, let's move down the hall to the next topic. Just click on that button that says 1.5 and 1.8 liter engines. Let's look at some of the 1997 technology used on both the 1.5 liter and the 1.8 liter engines. Both engines use a new generator for 1997 with a low noise fan that reduces interior and exterior noise. The ECM controls the generator output and resulting load on the engine to minimize quick changes in load at idle as electrical accessories are used. This results in lower exhaust emissions at idle. You've seen this type of generator on the Galant and Eclipse. To attain a high level of reliability, the timing belt core wire and the canvas have been changed to new materials. The timing belt width on the 1.5 liter engine has been increased from 22 millimeters to 25.4 millimeters. New fuel injectors have been developed for the 1.5 liter and 1.8 liter engines. These injectors are smaller and lighter than their predecessors. The injectors feature redesigned passages and a plate-type fuel metering jet. The new injectors are quieter, resist the buildup of deposits, help to reduce engine emissions, and improve high-temperature starting. The new idle speed control system used on the 1.5 liter and the 1.8 liter engines is the flow-limited control system used on Monteros with 3.5 liter engines. The dedicated wax pellet type fast idle air valve has been eliminated. A stepper motor controlled idle air passage is used for all closed throttle idle air control. A bimetallic flow limiter is used to control the maximum airflow allowed at idle as engine temperature changes. A new throttle position sensor with a built-in closed throttle position switch is smaller, lighter, and more resistant to engine vibration. Both engines use a new piston for 1997. The piston design minimizes the distance between the top ring and the piston crown. This reduces the amount of unburned hydrocarbons in the combustion chamber, resulting in more complete combustion and a cleaner exhaust. And a new cylinder head gasket is used on both engines. The gasket has been changed from a carbon material to a multi-layered metal gasket. This design decreases the volume of unburned gases trapped between the cylinder block and the cylinder head, resulting in less unburned hydrocarbons in the exhaust. The intake manifolds on both engines have been redesigned to increase engine breathing capacity by reducing the resistance to airflow through the manifolds. This was accomplished by using a straight port design. In addition, the general wall thickness of the 1.5 liter intake manifold was reduced from 3 millimeters to 2 millimeters, resulting in a weight loss of 30% over the previous design. The conventional solid flywheel, previously used with the 1.5 liter and 1.8 liter engines, has been replaced with a new flexible design. With this design, the crankshaft and flywheel mass are loosely coupled together using a flexible plate. This new design allows some types of powertrain noise to be tuned out of the range of the human ear. During normal service, the plate should never be separated from the flywheel. The fuel pump and engine control relays, which were previously packaged in a common case, are now supplied as separate components. The electrical function is the same, except the new relays can be serviced separately. You know how you have total control over the mouse? If you click on that button over there, you'll see that there's another sophisticated total control system around here. The engine and transmission total control system, which is used on other Mitsubishi models, improves the shift quality on 1997 Mirage models with automatic transaxles. This system reduces engine torque during transaxle shifts to ensure a smooth and positive shift. 2 new 5-speed manual transaxles are used on the Mirage for 1997. The F5 M41 is used with the 1.5 liter engine, and the F5 M42 is used with the 1.8 liter engine. Because of the new east-to-west mounting, both transaxles use a 2-shaft design instead of a 3-shaft design. The intermediate shaft and its components have been eliminated. This aids in weight reduction and noise suppression. To further reduce weight, both transaxles have die-cast aluminum cases. All transaxle sealing surfaces use formed-in-place RTV instead of gaskets. The transaxle case uses a plastic oil guide. A special bearing guide tap is used, and the case has a cutout for the tab. The clutch release bearing retainer design has been changed so that it can be replaced without disassembling the transaxle. During disassembly, be aware of 2 bolt locations inside the clutch housing. Inside the transaxle, a double cone synchronizer is used for second gear. This design allows more contact surface, which results in less shifting effort, less synchronizer wear, and higher reliability. To improve shift feel, the chamfered mesh points on the second and third gears have been modified to a one-way flow design. This design allows shifts to be made without interfering with the rotation of the synchronizer clutch gear. Gear shift control is essentially the same as before. Shift lever construction has been changed from the conventional 2-shaft type to a spherical rotary shaft fulcrum design. This new design assures a smoother shift. Power flow through the transaxle is similar to the F5 MC1. The F5 M41 uses a sliding reverse idler. The F5 M42 uses a constant mesh reverse. Now you'll provide some of the power by clicking on that button down there. Very smooth, I'm impressed. New model technology on the Mirage also includes the addition of 2 new 4-speed overdrive, electronically controlled automatic transaxles for 1997. The F4A41 is used with the 1.5-liter engine, and the F4A42 is used with the 1.8-liter engine. Because of the new east-west mounting, both transaxles also use a 2-shaft design instead of the 3-shaft design used in a west-east mounting application. The 2-shaft design results in higher efficiency and lower noise due to less moving parts and less weight. The hydraulic circuit consists of a front oil pump which is not serviceable and must be replaced as an assembly. 2 oil filters, which we saw in Part 1, consist of a spin-on external subfilter. Never install an engine oil filter here. And a main filter, which is not replaceable, except during a complete transaxle overhaul. Pressure ports for servicing, and 4 accumulators which help control the quality of the shifts. All shifts are made using a combination of clutches and brakes. There are no bands or sprags in these transaxles. Transaxle control is enabled through the use of 4 separate solenoids, which are duty cycled as needed to apply and release clutches and brakes to execute a shift. A 5th solenoid controls the torque converter damper clutch. Each solenoid controls the application of a specific friction element in the transaxle. These elements are the underdrive clutch, the second brake, the low reverse brake, and the overdrive clutch. When each solenoid is off, the related friction element is applied. Reverse is controlled through a manual hydraulic valve. During a shift, the solenoids are duty cycled to transition the friction elements from one gear to another. A friction element is completely released when the solenoid is on. Control information for the transaxle are sent by pulse generators A and B, now referred to as input and output speed sensors. They are designed so they cannot be accidentally interchanged. Instead of AC generators, they use Hall elements to generate outputs similar to a crankshaft position sensor. To provide the ultimate in driving comfort and precise control, fuzzy logic transaxle control that has been used with other Mitsubishi transaxles has been expanded with a new, intelligent and innovative electronic control system, or INVEX 2. With fuzzy logic, the transaxle modifies its shift behavior when traveling up and down hills as a result of driver inputs such as throttle and brake pedal application and vehicle speed. However, fuzzy logic is unable to sense the driving preferences of a particular driver. With INVEX 2, feedback and learning capabilities are added to fuzzy logic to modify the transaxle shift pattern according to driver preference. As the INVEX 2 system learns a particular driving pattern, it modifies its shift control pattern to favor an aggressive sporting driving style or a relaxed mellow driving style. In order for the transaxle to operate correctly, the TCM and all of its electronic components must be functioning properly. But if a problem should occur in the electronic control system, the transaxle will operate in fail-safe mode. In fail-safe mode, a TCM-controlled relay shuts off the power supply to all solenoid valves. In fail-safe mode, the transaxle will still operate in third gear and reverse, allowing the vehicle to reach a repair facility. 4 mechanical valves work together to ensure that the low reverse brake and second brake are not applied, since the related solenoid valves are off. A 3-position manual valve connected to the shift selector allows the driver to choose reverse, neutral, or third gear. If a malfunction causes the transaxle to go into fail-safe mode, the N-range light will flash slowly if the gear shift lever is in a drive gear. The service manual contains a list of conditions that will cause the light to flash. With the scan tool plugged in, the neutral light will flash out any diagnostic trouble codes stored. You can also observe DTCs by grounding Terminal 1 of the data link connector. Communications between the engine control module and the transmission control module enables the storage of OBD2 diagnostic trouble codes. Service data is available to monitor the operation of all 5 solenoids as well as other parameters. Actuator tests are available to actuate each solenoid during key-on, engine-off conditions. To assist in diagnosis, there is an actuator test to bypass INVEX and force the transaxle to shift conventionally. Now that we've looked at some of the components of this transaxle, let's take a closer look at how it works. Let's see how a friction element is applied gradually by duty cycling a solenoid valve. All 4 friction elements work in a similar manner. Let's look at the application of the overdrive clutch during a shift from second to third. In second gear, the overdrive clutch is not used, and so its solenoid valve is on. This blocks line pressure from acting on the overdrive pressure control valve. The pressure control valve prevents line pressure from being applied to the overdrive clutch. During a shift from second to third, the overdrive clutch is applied as the second brake is released. The timing of release and application of friction elements is critical to prevent internal transaxle lockup. Application is gradual for a smooth shift. As the overdrive solenoid is duty cycled on and off, line pressure to the overdrive pressure control valve is controlled according to the duty cycle percentage. The overdrive solenoid duty cycles gradually from 100% to 0%. During the time that the overdrive solenoid valve is off, line pressure is applied to the overdrive pressure control valve, moving the valve to the left. This applies line pressure to the overdrive clutch. As the solenoid alternates between the off and on states, the pressure control valve moves to control pressure applied to the overdrive clutch. In failsafe, when all solenoid valves are off, the manual valve controlled by the shift selector applies pressure to the overdrive and underdrive clutches. A hydraulic switch valve prevents line pressure from reaching the low reverse brake. The valve moves according to pressure from 2 hydraulic circuits. Failsafe valve A releases any existing line pressure on the low reverse brake. Failsafe valve B prevents line pressure from reaching the second brake and releases any existing pressure. Failsafe valve B moves according to pressure from 4 hydraulic circuits. Damper clutch operation is similar to previous automatic transaxles. The damper clutch has a dedicated control solenoid. Unlike other friction elements, due to the design of the damper clutch pressure control valve, the damper clutch is applied when the damper clutch control solenoid valve is on. Now let's take a look at power flow and elements in use during a series of shifts. In the P and N ranges, all clutches are released and power from the input shaft is not transmitted to the planetary gears. The low reverse brake is applied as a preparatory measure to make shifting into first gear or reverse quicker. In first gear, the underdrive clutch and the low reverse brake are applied. Power from the input shaft is transmitted through the underdrive clutch to the underdrive sun gear. Power from the underdrive gear is transmitted through the output pinion and tries to turn the low reverse annulus gear counterclockwise. The output drive pinion orbits around the underdrive sun gear to turn the output planetary carrier clockwise. Because the low and reverse brake is also applied at this time, the low and reverse annulus gear is held in place and only the output planetary carrier turns clockwise, producing the first gear ratio. The output planetary carrier transmits power through the transfer gear to the output gear and shaft and the differential gear and case. During the shift from neutral to first gear, the underdrive solenoid goes from on to off. All other solenoids remain as shown. The shift to second gear applies the underdrive clutch and second brake. In second gear, power from the input shaft is transmitted through the underdrive clutch to the underdrive sun gear. When the second brake is applied and the low and reverse brake is released, the reverse sun gear is stopped and the drive force from the output annulus gear causes the overdrive pinion to orbit around the reverse sun gear and the overdrive planetary carrier turns clockwise. Because the overdrive planetary is linked to the low and reverse annulus gear, the low and reverse annulus gear also turns clockwise. The amount of rotation of the low and reverse annulus gear is added to the amount of rotation of the output planetary carrier in first gear to produce the second gear ratio. During the shift from first to second gear, the low reverse solenoid goes from off to on. The second brake solenoid goes from on to off. All other solenoids remain as shown. Shifting to third gear, the underdrive clutch and overdrive clutch are applied. Power is transmitted to the input shaft, the overdrive clutch, the overdrive planetary carrier, and the low and reverse annulus gear. The turning speed of the underdrive sun gear, which is linked to the input shaft through the underdrive clutch, becomes the same as the turning speed of the low and reverse annulus gear. As a result, the planetary gear set locks and turns as a unit to produce a 1-to-1 gear ratio. During the shift from second to third gear, the second brake solenoid goes from off to on, and the overdrive solenoid goes from on to off. All other solenoids remain as shown. Shifting from third to fourth gear, the overdrive clutch and the second brake are applied. Power from the input shaft is transmitted through the overdrive clutch to the overdrive planetary carrier. Because the second brake stops the reverse sun gear, the reverse sun gear helps the overdrive planetary carrier rotate. This combined power is transmitted to the output annulus gear and the output planetary carrier to produce an overdrive gear ratio. During this shift, the second brake solenoid goes from on to off, and the underdrive clutch solenoid goes from off to on. All other solenoids remain as shown. The shift from neutral to reverse applies the reverse clutch and the low reverse brake. Power from the input shaft is transmitted through the reverse clutch to the reverse sun gear. Because the overdrive planetary carrier is held by the low and reverse brake, the power from the reverse sun gear turns the output annulus gear counterclockwise. Power from the output annulus gear is transmitted to the output planetary carrier to produce the gear ratio for reverse. Hydraulic power from the shift to reverse is applied through the manual valve. All other solenoids remain in the same state as in neutral. Well, that concludes the second half of the program. Having visited this web area, you are now a true veteran of technology. That's important because throughout the 90s, customers' expectations of service have continued to rise. The only way for Mitsubishi to meet these needs is through you, and your effort shows. You have continually improved your skills as cars have become high-tech. The 1997 model lineup will be a success because of our commitment to show customers that we have the expertise it takes to give them value and quality. We value it, and customers appreciate it too. Together, we will make 1997 the best year yet of the 90s. Well, you've done a fine job today. Thanks for helping. I guess you know what to do next.
Pix Productions, Santa Ana, California.